All right, everyone. Happy Monday. Welcome to another Wolfram Institute live science stream. We're continuing our conversation with Carlos about this thing we've been calling sub-axiomatic foundations of mathematics. Carlos, at some point we should come up with a candidate alternative name for this project. Not that sub-axiomatic foundations isn't a nice name, but there's probably a more accurate name that we can come up with. So we actually met somewhat recently to discuss this topic. And
Yeah,
I am aware that Carlos has been meeting with Nick and with Richard and other people to discuss a number of different issues. Carlos sent me an email on Friday when there's the issue of actually defining these various complexity measures for, well, I guess Carlos is saying even for ordinary graphs, but then there's also the matter of doing it for hypergraphs. And I think Carlos is suggesting to me that if we're able to do this effectively for hypergraphs, that in its own right, which for the purpose of this study is kind of a prerequisite, that would actually be a contribution in its own right, which on the one hand, it's always nice to find contributions to be made. On the other hand, sometimes we wish people had done this already so that we didn't have to do it ourselves. But it seems as though this might have to be something that we actually define for the hypergraphs, which is interesting.
yeah.
Another thing is that Carlos, so you said from your email, you're working on the translation of SK combinator rules into, yes, okay, into labeled hypergraphs. And then the final thing is to, yes, define complexity explicitly in terms of hypergraph metrics. Well, so, Carlos, we had a discussion quite recently. I guess the purpose of this call is to in part have a discussion that's, I mean, you sent me a very nice email summarizing everything from a few days ago. But just to understand in greater depth, are we stuck? Are there leads? Are there promising leads? Are there decisions like research decisions that you've made or you want to make? Where there are certain things you want to try? Are you trying
Yeah,
things? Are you
yeah.
still weighing possibilities on these different fronts? How is it going?
Yeah. So I thought, I think we have a similar mentality for this meeting because, so what I wanted to do is give a very brief overview of the stuff that I've been reading and the stuff I've been sort of trying to understand,
Okay.
which I think it's also a benefit for anyone watching that they can see what we are doing. And then yes, I think we are at the point where we have to, like, there's way too many possible directions where we can start to sink time into, and we have to be a bit strategic here. So I wanted this meeting to be like, okay, now it's pretty obvious what we want to do. I think we have a pretty good first direction, but or first, I guess set of goals, but we need to decide exactly where to go. Like, we need, okay, let's make this and this and this. Let's make these things precise while I keep on reading on this stuff, and let's do things
Yep.
computationally parallel
Yep.
to the theoretical stuff. So
Yep.
that being said, let me share my summary in
Okay.
this book. I hope this is visible enough. Let me make your faces bigger. Um, yeah, I think for people watching, that's fine. Right.
Okay.
So, so these are some excerpts from some of the papers that we are posting in this chats that we have in the suite, and so basically, I mean, I will not just go into the details of what's written there, but to give a sort of an overview, the first is to, well, consider the fact that from graph theory we do have complexity, or, well, entropy measures for graphs, right? And so basically, if you have the von Neumann entropy of a in the usual sense, you can use that notion to, given a graph, you define its Laplacian adjacency matrix basically by degree diagonal matrix, right? So the moment you have this L matrix, you can just do your spectral theory on it,
Hmm.
right? And so this von Neumann entropy down here, you basically just compute from lambdas. I mean, you can see that anything that's there is just the cardinality of your vertex set, which is some kind of
Yeah.
constant, not very relevant number, and lambda, which is the eigenvalues of your uh,
Hmm.
Laplacian matrix, which is effectively just the adjacency information, right? Because it's degree minus adjacency. It's a very straightforward matrix. So that's a possibility. The other possibility. So let's keep that in memory for a second. Then Shannon entropy is based on random walks, which turns out to be very similar to the von Neumann entropy, but it's in some sense it's conceptually very different, right? Because
sure.
These things are important when we want to generalize. We want to go to this higher arity or higher order.
Well, I guess the thing to think about is which one of these translates more naturally, or will be more tractable.
Yeah.
In the hypergraph case.
Which I would say, I mean, it's almost overwhelmingly von Neumann entropy.
Von Neumann.
Yeah.
Yeah.
And actually, I found earlier today, I found a reference where they actually use von Neumann entropy for hypergraphs.
Great.
So a bit of an overview of what people do in the literature. So what do people say about hypergraph complexity in the literature? This is a topic that's actually been kind of growing in the last 10 years or so. Like, it's not an old topic by any means. I mean, like anything hypergraphs, it's either very general combinatorics from the 70s, 80s, or only in the last 10 years you find any literature on hypergraphs, basically. So there's this concept of the line graph associated with a hypergraph.
Yes.
Which basically, I mean, by the way, the color code here is wrong. We had this discussion. We were very confused for a second that the color code is actually wrong in this figure because it's from this paper. But the algorithm is right. And basically...
Make your own version.
Yeah. I mean, this is very easy to make. So it's just here for summary. I mean, this is just summary of literature.
Sure.
So the idea, the core idea is that you take your higher order hyperedges, so your general hyperedges, and this is what I call an order reduction, right? Where you go all the way down, or maybe order projection, in which you draw as many lower order hyperedges as there are subsets of vertices in your hyperedges, right? So typically,
how are you defining the order?
Yeah, order is just in the traditional hypergraph setting is the cardinality of a hyperedge. So it's the number of vertices involved in a hyperedge.
Okay.
That's what I call the order. I think some people call it the arity of the hyperedge, but I really want to distinguish those two names.
Yeah. I imagine you do, right?
Yeah. So
yeah.
So order. I mean, some people don't even call it anything. They just say the size of the hyperedge.
Yeah. Let's just call it the order.
Yeah, order is good because order can be different than size in certain situations for some notion of size. So basically, if you have any given hypergraph which has mixed order in general, if it's not mixed, then it's called regular. Then you basically choose an order, say k, and you can effectively, if every hyperedge has order below k, do nothing. If it has order above k, then you can take all the cardinality k subsets of each hyperedge and just add that to the hypergraph, right? So that means that given an arbitrary hypergraph, you can get a rank k hypergraph. Rank for me means maximum order among your hyperedges, right?
Okay.
So you can get a rank k hypergraph from any given hypergraph. So the line graph is an example of a rank 2 hypergraph, which is just a graph, right? And I guess you always exclude the one edges because otherwise you get this always your elements redundantly. So in this particular reduction or projection, if you keep track of the labeling, then you are able. So effectively, what happens is that you get a lot of connections between vertices, but then you can also just simply characterize the adjacency of your reduced edges to be connections with new vertices. So effectively, what you can do is you can basically create a new vertex. You add a new vertex per hyperedge that you are reducing, and you draw a kth order hyperedge between the vertices and that new vertex, right? So in the case of the line hypergraph, everything is down to pairwise or binary, right? So everything is sort of like graph like, and so you have you start with 5 vertices here if you want to be 5, and then you end up with these many vertices in the end, right? Like you have I don't know how many more, like 10 or 12 more. So so that's because you need to characterize all the possible directed edges. If you want directed, maybe if you just want undirected, then you have as many vertices as you have hyperedges, right?
Okay.
So anyway, so long story short, you get from a hypergraph, you get a graph, right? And if you keep track of labelings, you are able to be one-to-one. You can always reverse this procedure. Now, this particular algorithm, which takes the adjacency, or I guess is it adjacency or I think it's the Laplacian matrix of the line graph of a hypergraph. They take that as the sort of adjacency information of your hypergraph, and they process your von Neumann entropy on that adjacency matrix. Now the problem is, of course, that the moment you put all this data into a matrix, you forget about the labeling. You're no longer you can no longer distinguish. So there is some loss of information. So you can no longer, from the so-called Perron-Frobenius, I think they call it, the Perron-Frobenius operator, which is this particular adjacency matrix. Oh yeah, sorry, it is the adjacency matrix, not the Laplacian matrix. Yeah. Just the adjacency matrix of this line graph. From that, you cannot reconstruct the original hypergraph because it's no longer labeled once you do matrix.
You already lose this information when you construct the line graph itself, right? Because you need the labeling of edges in order to reconstruct the actual hyperedges.
Yeah.
If you know the line graph itself, you also lose this information.
Correct. Yeah. I mean, yes, because I said that you keep the labelings in the line graph. Maybe that's why I didn't say that you lose the information there. But if you just construct the graph from the hypergraph, then yes, if it's unlabeled, then you've already lost the information at the line graph level, for sure. Anyway, so this is one way of doing it. And what's interesting about this particular approach is that even when they are losing information, they define what they call a complexity trace. And I find it interesting because, I mean, this is me learning about this subject mostly, but I find it interesting because entropy they define as a vector here. So it's not a collection of quantities, it's not a single quantity, but it's a collection of quantities. And I think that the main reason why they are doing this is that's what they call the complexity trace instead of just the complexity quantity period. And the reason being mostly that you have all these K's, right? Which are the layers centered expansion. I mean, there is some sophistication there, but basically because you have this higher order information, you can parse your graph in all these different ways. So you're effectively capturing order specific information. So just to give a sense of what's going on here, I mean, we can look into the details at some point, but is that we require more than just a number to characterize entropy. And that's kind of the gist that I want people to keep in mind. Now, the other approach is very explicitly the one that we started with, which is von Neumann entropy of the adjacency hypermatrix. But now the kind of price that we have to pay, quote unquote price, because maybe it's actually better, is that we have to use hypermatrices. And they call them tensors in this reference, which is obviously they are going to, because I think they're motivated by some graphics sort of engine kind of optimization problem. Okay. So obviously they're going to call them tensors. For anyone listening, these are not tensors; these are just arrays of numbers. But effectively, they're just matrices, right? So if you look at the definition here, I don't think I copied the definition of the hypermatrix, but they effectively define the adjacency hypermatrix just as I did last week. So basically, you have this higher order, higher dimensional matrices that you fill in just like your adjacency matrix for a graph, which happens to be rectangular or square, I guess, in the case of a graph. So you just have cubical, hypercubical, whatever, like this bigger stuff, higher dimensional stuff for higher order hypergraphs. So they do exactly this in the paper. So they define the Laplacian quote unquote tensor here just as the degree minus adjacency, same way. And then, of course, they have something I haven't copied here, but they have a section on spectral theory of these tensors, which is something that, again, I'm also trying to get up to speed with, because there is some literature, but the literature that there exists is very specific to, we're considering this particular product of higher order tensors or hypermatrices, and we're going to study all these kind of things. And if your hypergraph doesn't happen to behave in that kind of way, so connectivity in your hypergraph, then it's completely useless. It's like all these diagonalization algorithms they have, and they claim that they can run this particular polytimed better, whatever. It's all irrelevant, because at the end of the day, if you don't have that connectivity in your hypergraph, you're not going to find any of it explicitly. Anyway, so that's the other possibility. Now the other direction is, which is one of the comments that Nick made last week, and we discussed a bit further, is this idea that, so I think that at some point we do need a basic sort of relational measure of complexity. Like, it has to be something that, given 2, you get a measure that is relative, especially in the context of trying to capture complexity. Maybe in other contexts it's not so important. But so Nick had this suggestion of saying that maybe once we have a notion of entropy that we're happy with, something like mutual information will suffice to have something like relational complexity. I have a view that probably works, but I would rather see something like an explicit constructive notion of relational complexity being equivalent somehow, being shown to be equivalent to something like mutual information for a given entropy measure, or even deducing one of the entropy measures from first principles in a way. So one of the approaches that I have in mind, which would be one of the directions that we could actually computationally test out, is trying to go after the set of all possible hypergraph maps between 2 given hypergraphs, because we have a well-defined notion of hypergraph. These are essentially all the ways. I mean, intuitively, the idea behind this is you're going to look at all the ways that you can sort of put one hypergraph into the other, right? Mm-hmm. So this, for example, gets rid of the ambiguity. I mean, if you have 2 hypergraphs that are exactly isomorphic, right, then there's going to be just the relabelings of the vertices that you're going to get. So you're going to get something like cardinality of your vertex set, right, for the measure, which should be somehow like the minimum. But if you have something like very small into something that's very big, right, then you're going to have a huge amount of possibilities. Right. So
this is what we discussed last time, right?
Yeah, exactly. So it's kind of like something in that direction. So
okay, my question is just to perform a little summary of what you said so far, a little synopsis. Either we try and convert the hypergraphs basically into graphs in a somewhat lossy way, and then we use their Caron-Frobenius. It's not a Laplacian treatment in that case. It's like a Caron-Frobenius treatment, and we try and capture measure that way, or we can turn to hypermatrices. And so far as I'm aware, there's no hypermatrix built-in functionality in Mathematica. This would be something to be created. That would be a nice set of tools to have in general. But conceptually, I do like your suggestion, Carlos. The question is, do you have in mind application of anything that we discussed before your suggestion? Do you have any of those things in mind as techniques to be used when actually trying to assign a measure from a measure to these mappings, or do you have something else in mind? How are you actually going to assign a complexity measure to these mappings? I mean, I understand it qualitatively, conceptually.
So the idea is we have basically two fronts open at the moment, right? We have the hypergraph, the more abstract hypergraph front, which, by the way, I think this idea of hypermatrices for hypergraphs, it's almost inescapable in the sense that if you want to efficiently operate with hypergraphs, it's very likely that you actually prefer to encode them as just hypermatrices and never look back in some sense. But anyway, but that's a different question. The point is, we have this front on hypergraphs, and we have this front on labeled hypergraphs that are terms in rewrite systems that are going to be some formal system that we're trying to emulate, blah, blah, blah. So it's kind of a bit separate. Now, my idea is that if we have a strong, firm understanding of what hypergraph complexity is, in some sense, not the full story, but we have one that we agree, okay, this is representative of what we want to capture, right? I mean, we scouted the literature a bit, we saw that these are the possibilities, and we see some of the recent, there's some papers I couldn't access because they're not open, so we'll try to get access somehow. And I'll get to see what people are saying in the last couple of years about hypergraph entropy, because I feel it's quite a hot topic. And then once we are comfortable with that, which should take a couple of days, I mean, shouldn't take long. This is just a matter of finishing up the literature review. Then I would say that gives you a very obvious recipe to apply to the formal system emulation problem that we have in our hands, because once you have a way to assign hypergraph complexity, then you can just say, well, a rewrite rule is one hypergraph to another hypergraph. You can do something like relational complexity of input output, or you can just try and look at input context output and try to come up with some kind of weighted sum of this complexities, and it's very immediate that once you have that, you're going to essentially have a direct way of quantifying what is otherwise an arbitrary choice of, say, I mean, we could always do this length term length kind of measures like we discussed initially, right? Where you're essentially just counting the number of characters and you're counting the number of positions and so on. So the analog of that, which is string length, the analog of string length would be something like number of edges, number of vertices, whatever, like some kind of very superficial measure like that. But I think it's quite clear that that's not going to get you very far, because those numbers are a little bit arbitrary. Like how you count the size of a hypergraph is a little bit arbitrary. Like how you count repeats of labels and so on, it's a bit arbitrary. But if you have a strong definition of, or a strong agreement of, okay, this is the entropy notion that we're going to use, then it's just a matter of coming to terms with the fact that we have labels on top of our hypergraphs, which in some sense should just be some kind of quotient of our entropy notion, in the sense that the entropy notion is kind of pure blank applies to everything, right? And when you're labeled, you have these possibilities of duplicates, right? So it's just a matter, in a way, you could always, like, even if we don't figure out, for some reason, I don't think it's very hard, but if for some reason we didn't figure out how to assign complexity measures to labeled hypergraphs, we could always go to the skeleton of the labeled hypergraph and do the complexity on the skeleton. So even without figuring out the actual problem of complexity of labeled hypergraphs, we still have honest, systematic measures of labeled hypergraphs, right? Of course, they miss the label part, which is important in many of the formal systems, but you still get a number that is reasonable, right? Out of the rules. So my point of view at the moment is, if we agree, like basically I wanted to agree with you guys that this hypermatrix approach is better, that I should be taking the von Neumann entropy.
I agree.
Yeah.
I agree. Von Neumann entropy for the hypermatrices seems like the best approach to take.
Yeah.
And then what you'll do is, so we're going to express the rules themselves in terms of these hypergraphs.
Yeah, in fact, I have
we get three hypergraphs. We basically get left-hand side, right-hand side in the context. Still not exactly. I'm still not sure how exactly the context plays into the algorithmic complexity measure, but
it's really important. Let me actually just join with my
one thing to take into consideration, by the way, is so I think we can agree that if you have a mapping that's effectively an isomorphism, it's a rather trivial mapping. However, if the hypergraphs under consideration are still large, then you're still going to accumulate some algorithmic complexity because it will simply
But do you mean
it'll still require some non-trivial description length to even capture an isomorphism, even though the isomorphism is simple, it's still between these rather large graphs. So if you were just quotienting, that in its own right probably would be inadequate, because even an isomorphism between two whales would still be something.
yeah.
But then again, if you had something where it was a small graph turning into a whale, that would be much more significant, because as we discussed last week, you're really endowing your rewrite rule with the capacity to perform non-trivial work, which is a very important thing for algorithmic complexity to capture.
I wanted to make a little clarification, because the advantage I think that we have by doing this complexity of hypergraphs first before actually getting into the bigger problem or broader problem of rule complexity and so on is that this is not, I'm not I'm not getting allured by the simplicity of, a metric for a hypergraph, now I can run with it. This is just having some kind of measuring rod for these beings, for these kind of animals, right? So it's or like a scale and a measuring rod and a few things. It's not that this gives you any kind of ethology, right? Like the actual ethology is the rule application and the evolution. So I see algorithmic complexity. So something like the mutual complexity or the relative complexity of two hypergraphs that are isomorphic should be minimal, should be trivial, because that's kind of but this is the complexity itself, right? This is the complexity measure that is intrinsic to the hypergraphs. It's almost a tautology to say that, because if they're isomorphic, in some sense they are almost indistinguishable. Like you only distinguish it because your syntax is allowing you to distinguish it, right? It's just a sign that you might want to quotient by that relation. But if you
I just slightly disagree with it, which is, again, I think that if
but James, let me finish, because I think I agree with you, because the point is I'm just trying to somehow compartmentalize the process, and I'm just looking at hypergraphs purely, and then we look at the question of when these hypergraphs are being rewritten, and then you get a sense of algorithmic complexity. Because I think the traditional sense of Kolmogorov complexity and something like program length and this kind of thing for something like term rewriting, string rewriting, I think is a little bit misleading, because it's quite intuitive to think, if I need a string of this length and I put rules of this length and so on, so it kind of makes sense. So the analog in this very abstract setting of labeled hypergraph rewrites for formal systems, the analog of that is actually having chosen some rewrite rules, which are the ones that are going to take you different path lengths and so on, right? So in a way, the complexity of the algorithmic complexity for hypergraphs kind of requires of the rewrite setting for it to even be applicable, right? Because if you write a program for this is how I understand it. Maybe I'm confused, but in the Kolmogorov setting, to write a program, you need some kind of logic, right, to run the program with. So that logic is going to be some sort of rewrite system, right? Some string rewrite, some kind of computation needs to run, right? It's not kind of static cardinality based measure. It's more of a right.
But the algorithmic complexity is just describing the actual rule that's informing the computation. It's not taking into account the actual execution of the computation.
I understand.
Right? It's just it's just input.
Yeah. I understand it's that, but the way, so I understand that the algorithmic complexity is just looking at, say, size of program size, so to speak, right? I understand this, but the reason why that program is connected to your state to begin with, because you're assigning a metric to your state, is because you can run it and you can somehow compute it, right?
Yeah.
So my point is that once we have in the example of Kolmogorov complexity, you need a way to assign size, right? You need a way to assign complexity of this. This whole endeavor of hypergraph complexity is just to have a notion of that, because that's kind of the problem that we had. That you could naively just say something like hypergraph size of like counting edges and whatever, but it felt very inadequate. So if we have a good sense of, okay, this is what hypergraph complexity is intrinsically, then we can then say, okay, so when we have hypergraphs that actually flow into each other with a rewrite system, then we can apply exactly the notion of Kolmogorov complexity, where you have measures of complexity based on how hypergraphs flow into each other, but not so much about abstractly how they relate as hypergraphs, which is what I hope hypergraphs complexity should do. Like, I don't know if I'm making myself clear. I'm saying if you have two hypergraphs that are floating abstractly in space, like completely separate from each other, they are of the same species, right? They are the same kind of animals, so you can compare them. And the notion of relational complexity should apply to them. So some very universal thing, something like all possible maps between one and the other, or some kind of entropy measure to the hypermatrix, blah, 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 whatever. So that's just an intrinsic comparison, some mutual information of entropies or something. Sure.
Yeah.
But if these two floating hypergraphs that have no relation to each other are actually states, connected states, causally related states in a rewrite system with some rules, right? Then there's this whole question of, regardless of the complexity of the rules for a second, just the mutual complexity of those two hypergraphs, now it becomes relative to under which rewrite rules you're analyzing from, right? So I guess then you get the sort of pure intrinsic relational complexity, and then you have more something like an algorithmic complexity, which assumes some fixed rules. And then we can do what you've suggested from the very beginning, which is to say, now let's turn that analysis onto the rules themselves and the possible states that they can generate. And so you have this idea of balancing between the size or complexity of the rule itself, or the runtime and so on. So those, I think those metrics are dependent on on the rewrite system, because some of the metrics are literal runtime, right? Like the number of steps that you must take to rewrite one into each other and so on. So that's kind of where I'm placing it in the whole scheme of things.
Okay. Those are some interesting points. I'm a little slow because I'm resetting my sleep schedule, so I've been awake for a little while. So as I understand it, at least one point or one interpretation of some of the points that you made is that this impulse of mine to consider, for instance, the size, for lack of a better term, of the hypergraphs involved in the expression of this rule is something of a kind of an impulse to inherit something analogous to this string length measure that we would use in Kolmogorov complexity. But because we're not really doing that, we're trying to obtain a completely different kind of algorithmic complexity measure. Maybe instead of clinging to that kind of string length notion and trying to find an analog, maybe we could do something that is in some sense even more pure, in that we're encoding the actual rule as a mapping between these hypergraphs. And if we are somewhat agnostic to the hypergraphs individually, and we obtain a measure that's predominantly relational, then we're getting closer to capturing what's of real interest, including the way that I've been describing this trade-off between the algorithmic complexity and the runtime complexity, which is it's the capacity to endow the capability of doing computational work versus the performance of the computational work. And I can't think of a better way to encapsulate the endowment of the ability to perform computational work than having some non-trivial difference between the left-hand side and the right-hand side of your rewrite rule. If those hypergraphs are highly dissimilar, then wow, you have basically included as a kind of a pretension many steps that you would otherwise have to take into your rule itself. So yes, you convinced me. I think that a purely relational measure. So we're gonna try and get like a hypermatricial von Neumann entropic measure for these hypergraphs, and in the medium term, yes, we can apply them to individual hypergraphs, but that's just a means to an end.
Yep.
Once we're able to do that, then we're going to leverage that to actually develop a relational measure, and then we'll be somewhat indifferent to these measures as they actually apply to the individual hypergraphs. And you know what? I think that if it is a relational measure, in some sense, well, it depends. I don't want to be too defensive, but maybe this measure will be quite strong, even if we feel as though it's approximate. The fact that it becomes relational helps, because we're saying this is a complexity measure. You can debate whether or not it's a deep mathematical fact about these individual hypergraphs, but we can agree that once it's a relative measure, that it does nicely capture the kind of basic thing that we want to capture, which is when the left-hand side and the right-hand side of the mappings are quite distinct, right?
Exactly. Yeah. No, one thing that excites me is precisely the fact that the way I'm conceptualizing this, obviously we're going to make it hyper concrete because it will be computational. So eventually, but the one thing that is great is that this abstract relational complexity or the sort of relative entropy or whatever we end up finding, it's going to be something that is very universally defined. Meaning, by universal, it means that you do some kind of existence sweep, right? Like you go over all the existent maps or embeddings or partial motif occurrences, whatever, like some pattern matching, very general existence thing. And what the way I think this fits into the narrative that we have at the Institute with this rule approach to things and looking into rules and so on, is the fact that, you have this it's finite, but it's very universal kind of mess that's just, very bulky. Then within that you say, well, but if you look at these rules, which is the way I'm going to navigate this very large space, then I start to get these specific measures of complexity, right? So this is more efficient than this, right? There should be something like this is more efficient than that. We should find this in a very basic way, right? Like the fact that just adding one at a time, it's much slower than doing something like assembly, where you do add one at a time, then you have two, then you can do two at a time, and so on. Like these two things are very clearly intuitively different in that space of rewrite rules, but they accomplish maybe the same end goal, right? So clearly we're going to find different metrics for that because they are quantitatively different, right? In terms of the mathematics. So it gives me a lot of mental clarity. Like for the last week, I've been quite confused in general how to approach this, but like I think the last couple of days I've sort of settled on this, and after this conversation, I feel like I'm much more confident. Like, okay, let's push hard for this von Neumann entropy of hypermatrices, and then let's try to absolutely try to get the measures, and then we can start to. By the way, before we run out of time, I have some sketch of how to. Something I mentioned in the past, and I wanted to just visualize it.
Sure.
It's nothing too fancy, but just to before we.
Nick, do you have anything to say? By the way,
I was going to say. I was just going to ask Nick.
Yeah.
Well, nothing in particular. To just agree with all the points. Yeah, take the spectrum of your hypermatrices. I don't know. It's like, why not? We can. It's not necessarily the only option. We can explore all the options too.
Yeah.
I don't think they're particularly complicated to compute. Right? It's just what you actually do with it.
Well, I agree with Carlos that it's good to decide on some path to choose, at least as a hypothesis. Though I do appreciate Nick's kind of flexibility, where
I wouldn't decide pre-actual computing all of those.
Well, but I think Carlos's point, though, that he was making at the beginning, is that if we don't favor or privilege some approach, because this does involve, on the computational side, some work, including work that I imagine, Nick, you'll be doing, as well as some literature review. It's like we're either going to ask Carlos to wade through, one river or like 12. And it would be good for Carlos to try basically to go across one river. And if it turns out that that's not right and he has to go back, then that's fine. But just telling Carlos, yes, everything that you've suggested sounds equivalently promising. Wake up every morning and roll some dice and decide. That's not good leadership. That's not good. Not good coordination, etc.
Yeah, let me say maybe Nick was referring to something a bit more particular. I don't know if because I do think that we should focus, for example, this von Neumann entropy approach, which is based on the adjacency data that we have from the hypergraph and so on. I do think that we should narrow down in that direction. But maybe Nick was referring to the fact that the spectral theory of hypermatrices is kind of an open thing, right? Like it's not a closed subject like the spectral theory of matrices. Were you meaning more in that direction, that we should explore a little bit more what to do with hypermatrix in general, or?
Well, either way, you will do it. As soon as you want to compute some entropy, you necessarily will do it. And
For
I
sure.
don't know.
Yeah.
So,
I mean, I was not saying that we will have a single possibility of computational entropy, right? Like we'll probably have, because I mean the way you parse a hypermatrix for spectral theory can be done in many different ways. The obvious way is to slice it into matrices, right? So you slice it into matrices, and each matrix has its own spectra, and so that's kind of an obvious approach. But there are many ways of doing this. So we're going to have, even within my constraint, I think, is going to be, I want to do a von Neumann entropy approach to adjacency data of my hypergraph, right? And that's going to mean probably hypermatrix, adjacency hypermatrix. But within that, there's a fair amount of freedom that we have in how to extract the spectral information from the matrix, right? From the hypermatrix. So, and for that, I think we're going to have a few choices. I mean, we'll see what's most relevant and what is particularly useful, right?
yeah. Well, even besides hypermatrices, all the methods that you described, like from the papers, I haven't found them particularly hard to implement.
No.
It's like it's sure to just try it out. Okay, we can compute this thing from this paper. Okay, we can compute this thing from this paper. So just maybe do it for just to package it up, wrap it up with some function, just useful to have.
Yeah, no, absolutely. I mean, I was more voicing my approach. So James and people listening know what I'm going to be going down. It's to, because I mean, obviously I'm much slower developing the functionality side, but I think I make headway in the sort of more theoretical lines, and I just go and develop the theory. So I'll be clear to follow.
I mean, in terms of my own preferences, of course, I like it when fellows have options because this is experimental work. But I also like it when fellows have hypotheses, or given the options, there's one in particular in which they have a higher degree of confidence. If for no other reason that if they didn't have them, it would give the impression that, well, either philosophically they adopt a very skeptical point of view, or they don't have a strong belief about how what they're reading relates to what they want to try and do. And I think, what we just discussed between two of us, Carlos, it seems as though, yes, there are a couple of different ways in which this could ultimately be computed, but I think we have some qualitative conceptual idea of what we want to do, right? Yeah. So you have some conviction in what you want. You have some options in terms of how to do it is an asset. But it doesn't seem, these different options ultimately don't seem too diffuse from one another. It's really just a matter of practicality. Which one do you find is actually easy to implement, and also in terms of results and actually trying to capture this behavior and these properties that we conceptually understand. All right, now we are somewhat running out of time. We have another meeting technically in 5 minutes that involves one other person, which is Wukash. So I do like these sketches that you make, Carlos.
Okay, let me go over them in 2 minutes. Literally 2 minutes.
Yeah. Wow. Okay.
Yeah.
All right.
So this is just perhaps the benefit of the viewers, and to give a sort of a longer kind of week to week longer shot of where we're going.
Yeah.
So basically, this is the general idea we had. I mean, I had this idea a long time ago, but we are now starting to really get into it and implementing it. Where
Yep.
we have all this diversity. I'm mostly talking to the audience here. We have this diversity of formal systems that are, but because by the way, there are a few commenting and engaging, so it's nice. Hello everyone. So we have this very general formal systems that seem very different from the point of view of data structures, but it turns out that under this labeled hypergraph perspective, they become tractable under the same kind of universe of objects and the same kind of animal species. So in particular, in order to see what I meant when I said the label hypergraph representation of many of the rewrite rules are going to look somewhat kind of parsimonious and poor, you're not going to see huge differences. What I meant is exactly this. So you have your SK combinators. This is the usual term, place, value, whatever expression. You can see them as label trees, something like this. I mean, there's choice here. This is not the unique way that you can represent them, but this is some way in which you can represent them. You can also use, in fact, you can use higher order hypergraphs where you just use tuples and you know it can be different. But this is kind of the more, I think, evocative of Wolfram language, I believe. And then the rewrite again. Each right hand side, left hand side, it's a bit of freedom how to do it, but effectively you can read these brackets as some descendant in terms of taking input output. And so you can see that there is some generic, I mean, you should take S, X, Y, Z dot. Those things are just labels, right? So these just belong to some label set. And then what you have here is a graph. It's just a tree, right? Maybe it's a tree more than a graph. It has some internal order if you want. And then the rewrite is just this. This is one label tree. This is another label tree, right? So that's S combinator. K combinator is even simpler. You have one label tree into another trivial label tree, which is just one element, right? So these are the hypergraphs that we will have at our disposal to run these complexity measures. Obviously, these systems are very small in terms of rewrite rules. So doing some kind of higher statistics doesn't make any sense. But many systems have countable number of rules, for example, right? So it makes sense to have some degree of statistical distribution of complexity of your rules, right? When things are so small, I think it's very small. So I think it's very kind of poor in that sense. And then if you go to the algebra, which Boolean algebra if you like, which technically what we did was implement a unary involution and a binary commutative associative operation in a set of two elements, like not and. Then the rewrite rules are extremely simple in terms of trees, right? You get, I mean, the unary rewrite is basically just a label rewrite. I mean, again, there's choices here. You could do it differently, but if you are using labels, then it's just a label set map in a way. And then your and or become this simple tree to single term. So obviously this Z here is dependent on X and Y, because in these particular systems all your labels correspond to actual elements of your possible states. So this Z is exactly the matrix table of this rewrite rule.
Okay.
But anyway.
Okay.
So that's kind of where we're going. We want to eventually apply these complexity measures to collections of these rules, and particularly to these particular rules. Now, to make the context clear for everyone, if you have a very long expression that just simplifies, right, you could always take that as a rule, and this is where the complexity comes in. I think this is where James's suggestion comes in. You have a very long expression, like a complicated expression of Boolean operators and whatever, right? If you compute the whole thing down to the value, right, some truth value in the end, if you represent that in rewrite space, in the Boolean rewrite space, that might be big. If you represent that in SK combinator space, that is probably huge, it's enormous, right? The point is, you could make that into a rule, right? You could make initial state, final state, that's my rule, right? And it will make sense. It will be emulated by these other systems that actually take the intermediate steps. What we don't have at the moment that we're trying to find is a way to say, okay, So what did we just like give a different name? But how do these actually compare, right? Did we sweep under the rug all the complexity of the intermediate steps? Where did it go? So we're going to try to have some measure of that. So I think that's where sort of crystallizing.
Yes, exactly. Yeah. And the conjecture is, in that case, you've swept all the complexity into the rule. Exactly. Because it'll involve some, even in the hypergraph case, I imagine that some very complicated hypergraph then gets mapped to some much more simple hypergraph.
Yeah.
And the difference between the measures will be quite significant. So this is the idea, is that you can't hide the complexity. It will show up somewhere, either in the rule or in the behavior. Well, this was a very, I hesitated to hold another meeting so soon since we had met somewhat recently, but this was very productive.
Yeah,
and I think I've learned something from this, which is, I think in the past, I've wanted to give you and Nick and people with whom you're working some time, so that you had a few days to work on the steps that we had discussed before having another meeting. But really, I think that it's actually can be helpful to have a meeting only a few days later, so that if you're doing any kind of serious research and you're practical and you're strategic, you're going to find that there are decisions that have to be made. And if you want to discuss those with colleagues, then it makes sense to meet more often. So anyway, I think that I've learned a good lesson from this. Maybe we can even have meetings. We can even have meetings that are like half an hour long.
Absolutely.
We have another one like later this week that's like half an hour long, where it's like, hey, is there anything basic, any basic concerns or questions, et cetera, that have arisen in this research? And if we're meeting more frequently, then the meetings can be shorter. Basically, the description length becomes shorter, but the operations become more frequent. It's exactly what we're chatting about.
Some meta influence here. Yeah.
All right, guys. Well, we have another meeting to go to. Thank you to our audience members. I've seen. Oh wow! Look at all these comments. Yes. Well, hey, Vince Space. Thank you. Rmarks88. Nice to see you again. Prutz1311, also nice to see you again.
Yep.
I do see that there are some questions here, which I think we've neglected to answer. Why don't we collect these, Carlos, and we can answer them during the community forum? So Rmarks88, Prutz1311, and also Vince Spice, if you'd like to see your questions addressed, we'll be happy to address them during the community forum. That will be on Wednesday. You can attend if you're available, and you can ask follow-up questions, and we can have a dialogue. If you can't attend for some tragic reason, you can at least watch the recording later.
Yeah. So I just left the community link. So if you're not on the Discord server, you can join by just following that link. And yes, so you're very welcome to join live and ask those questions again, or maybe now they're fresh, maybe post them on the questions and comments channel that we have on the Discord server. And I mean, I will remember because this is an important question that you're asking, that how do you encode these higher rules? I mean, this is an interesting question, so I will remember anyway. But if you have some other questions, or in general want to know anything about what we're doing at the Institute and about ourselves, feel free to come onto the Discord and leave your comments. Good to have you.
Yes, and also now I'm looking at YouTube. I see that Memes of Destruction is here. That's great. Richard, I love that Richard, even though Richard is working for the Institute now, he's still fulfilling his historical role of being an active participant in the chats. That's great. All right, guys. Anyway, this was fun. I'll see you guys at the next meeting. And for our viewers, see you during our live streams tomorrow, and especially I'll see you at the community forum. All right. Chip, chip.
See you, everyone.